Hello everyone, welcome to my presentation. This talk provides new observations by the Geological Survey of New South Wales on intrusion-related gold mineralization centered on the Hobbs Pipe intrusion at Mount Adrah, New South Wales. Mount Adrah is located on the Gilmore Fault Zone in the central locline origin of New South Wales. The Gilmore Fault Zone is a terrain skew north-northwest trending structure and is a major tectonic feature in southwestern New South Wales. The locline origin is prospective for a range of deposit styles, including intrusion-related deposits, copper-gold porphyry, epithermal gold systems, and tin-tungsten deposits. The map on the left shows significant gold occurrences along the Gilmore Fault Zone. The Hobbs Pipe deposit is a main prospect in the Mount Adrah area. It contains about 770,000 ounces of gold and was suggested to be an intrusion-related gold deposit by Sovereign Gold Company. Hobbs Pipe deposit was first discovered in 1980 by geologist Roger Hobbs. It has been held by several companies since. In total, about 100 holes, including 11 diamond holes, have been drilled. Mineralization was identified to be centered on a pipe-like intrusion. The only mineral of value in the pipe is gold. The distribution of gold is remarkably homogeneous, and also a number of high-grade gold reefs have been identified in vicinity. The observations from the survey focused on Drillhole GHD009. Total depth is over 1,000 meters. As we can see from the surface projection and cross-section, this hole provides a representative section. It intersected the intrusive stock and metasedimentary host rocks, including high-grade reefs. New observations include petrology, hyperspectral data, and sulfur isotope. Now let's zoom into Hobbs Pipe deposit. The host intrusive stock is near vertical and concentrically compositionally zoned. The figure on the left shows early exploration data indicated the basic oval shape in plan view, slightly higher gold grades forming a concentric ring about the margins of the core. The figure on the right is a cartoon showing the interpretation of the relationship between gold mineralization and the intrusive stock. Three main phases have been identified: a felsic monzogranite core, an intermediate quartz monzodiorite to diorite outer core, and an intermediate to mafic diorite to gabbro rim. Gold mineralization is mainly hosted in the felsic core. Minor mineralization occurs inside the face boundary and at the contact with host rocks. Now on to the felsic core. It's predominantly composed of biotite quartz monzogranite to monzodiorite. Gold mineralization occurs mainly with disseminated pyrite, arsenopyrite, associated with sericite albite alteration. The thin sections here show alteration is typical and moderately intense in the felsic core. This drill hole was scanned using the HyLogger spectral scanner located at the W.B. Clark Geoscience Centre, Londonderry, New South Wales. Three mineral type plots show mineralogical changes near lithological contacts and alteration which relates to gold mineralization. In the felsic core, dark mica and chlorite is virtually absent, but white mica is abundant. The outer core is a diorite to quartz diorite to monzodiorite, with quite variable abundance of hornblende, as well as chlorite, muscovite, altered biotite, and proxime. The face boundary varies from sharp-sided to irregular, with evidence for mixing and mingling. Sulfides mainly occur inside the face boundary. Thin sections of face boundary shows chlorite, antinolite, after mafic phenocryst, including biotite. From HyLogger scanning analysis, mineral abundance plot show in the outer core. Dark mica is present. iron chloride is dominant, and white mica is abundant as well. The outer core is rimmed by dark composition. These rocks are intermediate to mafic. Within the outer core at the contact with the rim, there is about a meter-wide zone of gold mineralization, which is associated with pyrite, chloride, sericite, carbonate alteration. The thin sections here show mineralized vein at the contact between outer core and rim, and also show the mafic rim. The contact with host rocks is irregular and intrusive. On the right-hand side, mineral abundance plots show in the mafic rim, white mica is much less abundant, but increases near the contact with the host rocks. The host rocks are foliated, mafic to ultramafic metasedimentary rocks, where around the fractures close to the intrusive contact, there are narrow zones of more intense sericite carbonate alteration with minor gold mineralization. The photo at the bottom shows the host rocks are cut by mineralized quartz carbonate sericite veins. The veins are zoned with calc-silicate selvages, which is shown in the thin sections. Again, from the hyperspectral analysis, white mica is mostly rare in the host rocks. Abundant white mica is associated with lithological changes within the host rocks. Let's continue to follow this drill hole. Within 500 meters from the intrusive stock, there are a few quartz reefs with high-grade gold. The reefs contain low abundance of sulfide minerals. Sericite carbonate alteration occurs at selvages a few meters wide to reefs. In photo B, we can see narrow quartz veins have similar alteration selvages. Their width is roughly proportional to the width of the vein. On the right-hand side, mineral abundance plots show iron chloride is dominant over magnesium surrounding high-grade reefs. White mica also increases at selvages. So to summarize a hyperspectral analysis, we can see inverse abundance of light and dark mica occur in the felsic core, near phase boundaries within the intrusive stock, around the gold-bearing reefs, and near lithological changes within the host rocks. So they suggest white mica replaced biotite-rich dark mica. Iron-rich chloride and carbonate are a feature of the alteration, which is related to gold mineralization. As part of our study, we did 28 sulfur isotope analyses on sulfides. As you can see from the plot, the results mainly fall within a relatively narrow range, although we can see slightly variable results from near the phase boundary and contact. But overall, it doesn't show inverse negative zonation towards the core of the intrusion. So the results for high-grade reefs also fall into a similar range with the results obtained for the felsic core of the intrusion. So this possibly suggests a single magmatic dominated source of sulfur. So if we put all the data information together, this image shows correlation of spectral plots, assays, lithology, and our observations. So this is a great visible way to connect all the dots. So we can see the most striking changes in the hyperspectral images are associated with different lithologies. Alteration is more intense near lithological changes and at the margins of high-grade reefs. From our observations, we can use this cartoon to interpret the intrusion emplacement and mineralization processes. To recap this talk, new observations suggest that both the disseminated mineralization within the core of the intrusive stock and the distal high-grade reefs are related to the same mineralizing event. As we know that the overall underlying feature of intrusion-related gold system is the direct genetic association of mineralizing with a causative pluton. The gold mineralization at Hobbs Pipe and in the reefs conforms to the concepts for intrusion-related gold system by Phil Blevin. Also, we published the GS report. If anyone is interested in more details, feel free to have a read. Thank you.